as I mentioned earlier, acoustics is really just a tool for understanding population structure. And I want to talk a little bit about one tool we've developed, a little bit to talk about the tool, but a lot of it is actually to start keeping in mind the idea of developing flexible tools or processes or techniques to address these complex questions. We each have our own method to working with our data, but if we can develop tools that are flexible, that we can, more than one of us can use, it'll help all of us, I think, in adapting and developing to the point where we can actually apply our data. They need to be flexible because the technology is rapidly developing. There's new widgets, new measurements, new ideas coming through faster than any of us can react. So at the very least, we want our tools and our techniques to be able to adapt to those new technologies. And the questions that we're trying to work with are applicable to a wide array of species and environments and situations. And so it'd be nice if some of these tools were also applicable to a wider variety of species and environments. And so the fewer independent wheels that we create, then the more we can kind of work together to actually push the science forward a little bit less spinning of the wheels. And so having said that, this is my wheel. Like all of us, we have to collect our data. Most of my data has been collected at sea on ships, but it doesn't matter where it is. They could be autonomous recordings or handheld, whatever. We all work with recorded data. That's what we have. Sometimes we have other data associated with it, visual observation, GPS. Then we need to analyze it with the acoustic side of things. My tool primarily is PAMGuard. It's written for working with marine mammals. That's its history, not necessarily its destiny. And I happen to like it because it's flexible and modular. And then once we've done our basic acoustic stuff, we've gotten our detections, we've grouped them, localization, we then need to do something with the data. And so everybody's written their own routines to deal with their data. We're trying to develop our routines in R packages so that they can be open source and flexible and available for other people to use. And so right now we're developing two packages. One is we call PAM-R, PAM being passive acoustic monitoring, and R being R. And that does a lot of the housekeeping. It puts our data together, formats it, brings in environmental data, visual data, runs some measurements on our calls, and does everything with a couple pushes of the button, we hope. One of the packages that we're putting as an independent package that I'll speak on here is we call BANTER. It's our acoustic classification scheme. And I say scheme because Eric did it, and so it's really quite the scheme. And BANTER is an acoustic event classifier. It's not a call classifier, really. It's got that as a component, but it's an event classifier. And that's important for the work we do because we encounter a dolphin school, who is it? We encounter a whale school, who is it? Some of these we see, some of these we don't. And so we're talking about supervised learning here. And then the intention is that we will finally someday, after working in this field for far too long, you'll be able to apply this data. And so this is our general workflow. But some of the features about this workflow that I think are important, they're important to me, and I'd like us to keep it in mind as we talk this week, are that when we develop tools that are free and open source and other people can use them, I think that's helpful. Everybody goes through school working with MATLAB because they offer really low prices to students. Everybody gets everything in MATLAB, and then you go to the government and there's no money, even with our government. And so, so I'm trying to translate a lot of actually Taiki's translating a lot of MATLAB into R right now. It's also flexible and modular. Somebody creates a new widget, you can add it in as a function. You don't have to rewrite a whole bunch of stuff. And the stuff we're developing also general. We apply it to dolphins and whales, but it really doesn't matter. It's just for acoustic data. And so BANTER itself, I want to just kind of run through it real quick, but I'm trying to look at it in the framework that it's a flexible tool to address these complex problems. And before you get into BANTER, you had to get some measurements. We're using PAMGuard and this PAMR package that we're doing to get our measurements. We do a lot of auto detection and classification. Not classification, auto detection, and then lumping them, the human has to put them into groups, and that's really a bit of our sticky point. And then we run a bunch of measurements. Once we have our measurements from a whole bunch of different detectors, and these can be very generic detectors, we then throw them into BANTER. It's a two-stage classifier. Stage 1 is a call classification, where we're working with these detectors. And then stage 2 is where we put all that data together to say, what is this group, what is this event? So on the call detection, we're kind of taking a few steps back and getting fairly generic. If we talk about a dolphin school, we might have whistles, burst pulses, and clicks. But if it's a beaked whale school, it might just have clicks. And we found that if you just take one of these detectors and tweak the settings, it views this acoustic landscape completely differently. And so, and that's kind of how I view these detectors, is each detector is a different view of this acoustic landscape. So our first run of a burst pulse detector was really just a few tweaks different from this. It did a little bit better at these burst pulses and a little bit less well with whistles. And same with the click detectors. A few little tweaks of the settings, and then it behaved very differently. So for each of these, we get some number of measurements, whatever's appropriate for the call type. And so then we end up with just tables of data. So for each detector, we get a table of data. Each row is a detection, a call, so maybe a click or a whistle. And you get a bunch of measurements for it. And what we're working on is an event classifier. So in training this data, we need to have each call associated with an event, or even regardless, even if you're doing a prediction. So each call needs to be associated with an event. And for this one, we are supervised learning, so we need a species ID for building this classifier. But anyway, it's fairly basic. We just have a bunch of detectors. We've run through our stuff. The person has to go through and pull out events. That can be a little messy. But then we just basically, the rest of it's spitting out this data. And that part is mostly automated. And then we apply call classifiers to each one of these detector data sets. And the call classifier we're using is random forest, which is an extension of the classification of regression trees. But CART, for CART analysis, you might have one result. One tree equals one result. But with random forest, you're running this tens of thousands of times, and you end up with a whole forest of trees. And so for every decision, or for every tree, you have a decision. So you have a lot more information to work on here. So this is at the call classification stage. And usually when you're looking at a classifier, you might look at the confusion matrix. Here an example, our SC is our striped dolphins. And this would be our correct classification. And often this is kind of where we stop and go, what's our correct classification? And here it's just kind of mediocre in general. But there's a lot more information here, and we want to take advantage of this information. So correct classification is only part of the story. We also have this probability of assignment to a whole bunch of different species here. And there's information and value in that. And if you look in our whistles, most of the misclassifications were to these DC, DD, that's our common dolphins. But over here in the burst pulses, misclassifications were pilot whales. And over here is pilot whales and killer whales. So there, you also have differences across these detectors. And all that information is really valuable. And we can take it to this next stage of looking at the event. So taking those results, but looking at it from a data point of view, we have a call from an event, and it's a BP, so it's a burst pulse, and then we have this probability of assignment to each species. And then we do it for all calls, all burst pulse calls from that event. And what we can do from there is calculate a mean assignment probability for each call type in each event. And so a lot of this process is fairly simple. We're taking the human out of a lot of it, and we're getting the distribution of the assignment probabilities. And we're very imperfect at this stage, and that's okay. Because then we can take this data to the next stage and do the event. And we have some number of events, and when we're training the data, we know the species ID. So at the event classification level, we have our mean assignment probabilities, and that's all the fundamental information from our first stage. Then we can add in some event level information, call type, whistle rate, environmental features, water temperature, things like that. And then we run random forest again. So this is just a hierarchical random forest classifier. And so BANTER is fairly new. We've run it on 2 different data sets. We've got some dolphins and some beaked whales. Beaked whales only produce clicks for the most part. That's all we detect anyway. And so I just did a few different click detectors there. And just generally our results were pretty okay for the dolphins, between 71 and 92% correct classification overall at the event level. And there's a million ways we can improve this. But to me, the important part are these 2 right here. This is 2 types of common dolphins. And I never, ever, ever imagined that we would ever be able to differentiate them at all. But because of these results, I have pretty much faith that at the event level, we're okay. We've got a method we can work with. Just last month, we ran it with beaked whales, and our classification scores range from 89 to 100%. This is actually on super preliminary measurements. We didn't even have measurements of some of the key characteristics, and yet it still worked well at an event level. And this is on animals that only do 1 click type. So this gave us hope that we can apply it to animals with low call diversity. So our general classification scheme seems okay. We've got a very flexible approach. We can throw it at different species, work with different data, but we also need to improve it. It's very imperfect. And one of the questions we want to know is how strong were those classifications. Each event classification we did, we ran at least 5,000 trees, and not all of those trees voted for the right species. So we've got some visualizations to help us understand that. And in these plots, there's 1 for each species, and in a vertical slice, that would be an event. And the color is the kind of like the proportion of votes or trees that kind of voted for that species. So you can see different events had different strengths of their classification. Now, if they were all perfect, it would look like this, and that would be really nice. And we're never going to get there because the animals are uncooperative. But we can get close. And like here with our Delphinus, this is supposed to be the bad guy, but we had a lot more data here to train with. And it's largely peach, which is the right color, right? But once we get to this level and we can improve our classifications where we're not only correctly classifying, but strongly classifying, then these ones where they're wrong, we can really start to learn from that. And we can start to say, well, maybe it was a mixed species school and they just didn't see, a few little striped dolphins mixed in there. Maybe we had contamination from another school nearby. Maybe it had a different behavior. Or maybe it was a little bit of a different population, that not all common dolphins are created alike. Maybe there's some other group that produces sounds that are a little different. So anyway, we have some visualizations that we can start to ask questions about our data. And so with the approach that we've developed, it's flexible also in that we can incrementally improve it. Clearly, adding more data is number one. But we can also just create new call detectors. These can be very generic. We can just tweak the ones that we already have and rerun it through our same data. We can create new call measurements. We're working on this with the beaked whales, and to do measurements that help us better clarify them. And we can add more event level data. And hopefully then we can apply this approach to other species and other questions. Just real quickly, this is going to be available publicly on R later this summer. It works best, you should have multiple call detectors, but it only requires event ID, species ID, and your measurements. As you were saying, you have to have data. You cannot have missing data. That is a non-starter. You can build your classifiers, then predict on them, and I hope we'll have an unsupervised mode eventually. That's how I keep him on a tight leash. Some important caveats. This is one tool for one thing. It's an event classifier. It's not that good at a call classification. When you want to then apply it, if you built this on apples, you have to apply it on apples. If you have water temperature in as one of your variables, you need it on your novel data. You have to be very, very careful of the context, because this does take in a lot of context about what's going on with that overall event, and so you have to not misuse it. So BANTER is one flexible tool for solving these complex problems, and one of the things we want to think about in the next few days is how we can develop things in a way that work for the bats and work for the dolphins and work for the insects, and approaches and techniques that are flexible in that way to work for all of the problems and questions, or at least some of them that each of us are encountering. So that's it. Thanks.
I really liked how you were taking those, you were sort of constructing features based on the calls, I believe it was, and then using those to classify the events. Is that correct how I'm interpreting that?
Yeah.
Yeah. I thought that was a really great idea, and it was really nice to see some of the results that you're getting. I had a question about your labeling. Since you mentioned this is supervised data, I'm totally unfamiliar with the challenges of actually, you sort of alluded to the fact that it was very challenging, very noisy process, and I was wondering if you could speak briefly on the challenges in actually labeling events correctly prior to the machine learning.
Yeah, our data is different than many. We spend those months and months at sea, and we have real-time visual observers and real-time acoustics people going through, and we mark out events, we localize and determine if they're the same or different. And that, a large part of that is done in real time. With some species like with the beaked whales, there's some species who an encounter with them is very finite. And so you get them for a minute, and you're like, okay, that's easy. When you have a dolphin school and you are with them for a half hour, an hour, that's a totally different thing, and that gets really ugly. And when we're in the middle of them, I just basically say, I'll take a half hour when we're in the middle, and I know it doesn't overlap with anyone else. And so that's not pretty. And it's imperfect. And so if we were doing an autonomous recorder and doing dolphins, and that's the kind of stuff that Marie has to work with. It's a different beast, and it's hard. And the defining a group is really, really tricky, and there's a lot of assumptions that go in it. I'm lucky that I have overlapping visual and acoustic data and localization. And so I can say they were the same and not different.
You very briefly mentioned context at the end of your talk, and I think that's a really important feature set that often gets overlooked. Can you just talk a little bit about the context variables that you include and how you think context is important?
Yeah, we've done almost nothing on the context. I just put that in water temperature as an example. We haven't done any environmental variables yet. We are going to, but we've decided not to use our in situ environmental variables, for example, because if we collect them on the ship, there's a lot that goes into that and into calibrating it and whatnot, and takes a really long time to get that data. And so I know that when I want to predict, I'm going to be ready before I can get that data, and I might not get that data because we keep losing our environmental team. So I'm going to be going through online resources where I know I can get data in a more standardized way. That's for that. When it comes to other things like the proportion of call types, that also you have to be a little careful of, because it depends on at what point there's a difference between when you're in the middle of the animals versus when they're far away. Far away, the low frequency sounds come to you, you get fewer of the high frequency. So you have to make sure that you're treating them fairly equally. Same thing with a lot of the work, actually, I want to talk to you about your vertical sampling of the recordings for classification. With us, in this 3D environment, it's kind of like, if you have the insects high on the tree and low on the tree, or gibbons or whatever, it's the same with us. That what we detect is going to depend on where the animals are in the water environment. And so our towed array data is not applicable to Marie's, seafloor data. It's not. We hear different things. It's also our daytime data is not applicable to night because they do different proportion of calling. And it goes on and on. Daytime is for daytime. Seafloor is for seafloor, that kind of thing.